Hi, my name's John Taylor. I'm a biologist here at Southern Utah University. I study bats, and I'm also very actively engaged in science education in both the state of Utah and in the United States. What I'd like to talk to you today about are some of the new movements in science education within the United States and the state of Utah. And ultimately, I will lead you through these changes and give you an example of one laboratory experience that I use here at the university, but I've also used in the high school setting and the middle school setting, so that I know that it works with kids at least 10 years old or older. First off, you need to understand who actually decides what it is that we teach as teachers. And it'll be different in the United States based on whatever state you happen to be from. In Korea, I'm assuming the government plays some type of a role. Maybe some of the decisions are also done locally as well. In the United States, there's multiple groups that come together that help us decide what we would. There's multiple groups that help us decide which areas of science that we should concentrate on. Those three areas are educators themselves, researchers in both science education as well as in just the general sciences, and also employers inform those decisions. In the United States, there are two large groups of scientists that really do most of the informing on what to teach in a class. The first group is the American Association for the Advancement of Sciences, or the AAAS. This is a group, a large group, composed of researchers from all over the world, actually. And who better to inform what science teaching should look like in the classroom than actual scientists? A similar group is the National Research Council. In the United States, the National Research Council is also a group of scientists. Sometimes these scientists are also members of the AAAS. But these scientists have a special mandate, and that is they provide scientific information and understanding to government leaders of the United States. And then finally, the last group that is mentioned on my slides is the National Science Teaching Association. This is the nation's largest association of teachers, specifically aimed at helping those teachers teach better science in their classrooms. Together, those entities present the latest and greatest ideas on scientific education practices. But it still comes down to individual school districts within the state, as well as sometimes the state makes that decision. So it really depends on where you are in the United States on that. But still, at the end of the day, somebody is making a decision on what content, what scientific content is being taught in those classes. And you need to understand what that content is. Now, when you're thinking about the scientific content, you should ask that question of, well, why? Why am I teaching this one particular piece of science? Why not something else? What's the point? Well, a few things you should consider. First off, I've got a quote from Louis Agassiz, who was a distinguished Harvard scholar, a natural historian, clear back in the 1800s. And he once said this, that facts are stupid things until brought into connection with some general law. What that means is that just memorizing individual scientific facts is not what science is all about. And in fact, that practice of just memorizing and restating those memorized facts really isn't that great of a learning experience. For the students, it's not fun. But also, it's not the kind of learning that's going to translate into higher level thinking skills. If all we do is aim for the remembering stage, which is at the very bottom of Bloom's taxonomy, we're aiming too low. we need to get our students to not just remember things, but to start understanding them, then applying that understanding to new areas. And then on top of that, what you really should aim for is creating an environment where the students can both create their own scientific studies, they can evaluate those data that come from those studies, and that they can analyze it. Now, you can't just jump to the top of this taxonomic scale. You do have to have some basic facts that are then understood, and it builds as we go up. The key is, though, the higher you go, the more fun and the more engaging it is for the students and the teacher. So you want to get up as high as you possibly can. Now, in the university setting, our freshmen typically will have courses that dwell mostly on the remembering and the understanding levels. But that doesn't mean that you can't take little brief journeys up into the application or maybe creation, evaluation, or in analyzing data. But as the students get older in their sophomore year, junior and senior years, those courses should spend more of their time on the upper end of this taxonomic scale. Now, some of the recent changes in the United States in science education are what we call the next generation science standards. Now, where this came about is some of those groups that I mentioned earlier, the AAAS as well as the NRC. Both of these entities independently about 20 years ago came out with guidelines on what they thought science education should look like in the United States for the next 20 years. Each of them were different from each other, but they also had some similarities, a significant amount of overlap. But each of them also had problems. As good as they were, there were issues. And in the 20 years since they came out with those first two main guidelines, they've worked together as a team to cut off all the bad parts and to accentuate the good parts. And the next generation science standards is the result of those two entities working together. What they have done is come up with what we call the 3 domains of science. So that's 3, think of it as like 3 pillars that hold up science education. And those 3 pillars are of equal importance. And we need to make sure to build into our classrooms the ability to have all 3 of those domains working in the lives of our students. So the first domain that's easiest to understand is the content. Well, the content has been around forever. We've always been teaching science content. But what's different in the next generation science standards is hundreds and hundreds of scientists argued over what are the key content areas, those disciplinary core ideas that every student should be able to understand. That meant cutting off some of the old science content that's been around for decades. Now, when they proposed cutting off some of that old scientific content, there were a lot of people in the United States that struggled with that. But again, their hope wasn't just to teach facts. It was to help students learn how to do science by doing science. So the disciplinary core ideas is our first pillar. And that has greatly reduced the amount of scientific content that you'll find in an American science classroom. The second domain is the skills and practices used by scientists and engineers. Those science and engineering practices are what the students should be doing in their classrooms. By letting the students do the very same things that scientists do in their research labs, students will better understand what it is that it takes to do science well. And the last of the 3 is the cross-cutting concepts. And that was the newest addition to the next generation science standards. That was somewhat present in those original guiding documents from 20 years ago, but they have been brought to the forefront, and teachers are being instructed on how to bring those into the classrooms right so that they have equal standing with both the content and the skills and practices. So I'm going to go through these, and I don't expect you to know everything about them. There's a lot of information that you could read to get more information about these, but I just want you to want to make you familiar with what they are. First, we'll hit those science and engineering practices. Now notice again, these are things that students should be doing. The teacher should not be jumping in and doing this for the students. So number one, students should be asking questions and defining problems. That means the teacher shouldn't supply the questions. The students need to ask their own. One of the main reasons for that is, yes, scientists ask their own questions, but also when you ask your own questions, it means something to you. And when it means something to you, you take ownership of it, and it becomes important to you. It's not something that somebody else is trying to push on you, it's you pushing yourself. Super important. Number two, students should be developing and using their own models. Now, models in this case could be models just that they create in their mind. It might be models that they draw out. It could be models that they're making with art supplies or something. These models help students understand scientific principles. Number three, students should be planning and carrying out their own investigations. That means really redesigning the classroom. Number four, students, when they're doing those investigations, should be able to analyze and interpret those data that are collected. Often in science classrooms, at least in the United States, that step is often jumped over, or teachers help their students a little bit too much with that. Number five, tied to number four, using mathematics and computational thinking as a way to analyze and interpret data and to carry out those investigations. Number six, students need to be constructing their own explanations for phenomena that they are investigating, or designing solutions if you're trying to do some type of an engineering project. Number seven, students should be engaging in argument from evidence. And when I say argument, that's not fighting or bickering inside of a classroom. It's students in an engaged discussion with each other about possible explanations or patterns that they're seeing in their experiments. And they're using the data or the evidence from those experiments to talk about what's really going on. Sometimes they may have conflicting ideas, but that discussion is incredibly helpful, and it's something that scientists do all the time. So why not help our students learn how to do the same thing? And finally, number eight, again, it brings it kind of all together. Students should be obtaining, going out and finding their own sources. They should be evaluating those sources and then communicating information. That last one often also is skipped over in the typical American classroom because it means letting your students talk. And that takes time. And in some schools, they just don't have enough time for science. But throwing in this communication piece is incredibly important because, again, it's modeling what scientists do normally. So there's the science and engineering practices. Now, in one particular lesson, or maybe unit, a group of lessons put together, you're not going to do all of these. You have to pick and choose based on that particular lesson, and they need to be grade level appropriate. You couldn't expect kindergartners to analyze and interpret data in the same way that a 15-year-old student could. So you have to be able to adapt this in a way that's useful to the grade level in which you're working with. On to the second one. Oh, let me back up one piece and illustrate this. The other reason we're doing this with these science and engineering practices, again, stressing students are the ones who should be doing this, and what we're trying to do is avoid cookbook laboratory experiences. And what I mean by cookbook laboratory experiences is often in lab, the teacher has laid out all of the steps that students should do. And the students don't have to do any thinking other than just following those directions. And if they follow the directions correctly, they will get an expected outcome at the end of the lab. The assessment would then be, well, did you see what you were supposed to see? And if not, well, then you did something wrong. The problem with cookbook labs is, again, it's the teacher kind of forcing an idea or a process onto the student. So the student doesn't really take ownership other than the fear they have of making mistakes. But next generation science standards should embrace mistakes, and you'll see why in a little bit. The next is the cross-cutting concepts, and if you remember, I said that these, to me, were the most important thing that came out in the NGSS standards. We're going to break these down just a little bit. So there's actually a number of them, but I've grouped them together for a very specific reason. These cross-cutting concepts are exactly what we mean. They cross-cut through multiple disciplines. So for example, these cross-cutting concepts are just as applicable in biology as they are in geology or oceanography or physics. It doesn't matter the discipline. These things are important ways for us to help our students see and understand the world. You'll see why in just a second. So number one, patterns. That's what we do in science. We gather data from doing either observations or experiments, and those data have a story, and we have to figure out what that story is. These patterns or phenomena help us make sense of the natural world. And sometimes the pattern might be cause and effect, meaning that we can draw a clear line between we see this phenomena because of this. The icicles are melting on the building because the sun is shining, or something like that. Finding these causes and effects can also help us with predicting things into the future. Now, both of those cross-cutting concepts together do something that's pretty important. Hopefully it tells the student that the natural world is knowable. We can figure this stuff out. And when we apply scientific processes, the whole goal is to understand these phenomena. Moving on. The third cross-cutting concept is scale, proportion, and quantity. This is that mathematical piece that comes out. And essentially all that we're trying to help the students understand at any grade level is that math can help us understand the story. Sometimes that's through making tables or designing graphs of some sort, but helping students understand the natural world through the use or the language of mathematics is a huge step, which often goes neglected in the United States typical science classroom. Numbers 4, 5, 6, and 7 all work together, and they actually are all tied together by number 4, the systems and system models. We need to help students get rid of the extra stuff that's around them. There's always so much that's kind of clouding our judgment or hurting our ability to understand what's going on. Scientists are really good at getting rid of that extra stuff and defining what a system of investigation is and focusing just on that system or that system model. Numbers 5, 6, and 7 all help us define and understand that system once we have it. So for example, energy and matter. Students need to be able to focus on a system, whether it's the human body or a cell, or maybe even just a mitochondria that's doing cellular respiration, and be able to track the flow of energy through that system and the transformations of the energy as it's going through that system, as well as the cycling of matter. And it's very important that you understand, I chose those words carefully. The flow of energy through a system and the cycling of matter. The next one, number 6, structure and function. This relationship is key, especially in biology and engineering. In some respects, it is in chemistry, but a lot of the understanding about living systems can be made just by using structure and function. And you'll see what I mean in just a few minutes. We're actually, the experiment that I'm going to lead you through uses structure and function and scale, proportion, and quantity as the cross-cutting concepts to help us understand a biological principle. So you'll see those in action in a few minutes. And then the last one is stability and change. A good example of stability and change would be the entire field in biology of ecology. But it can also extend to something like faults in earthquakes and plate tectonics. It could be how your heart and your heart rate and breathing rates change when you're exercising, and how that change then leads to a stability of heart rate and breathing rate. These cross-cutting concepts can pop up in any of the sciences. So again, why are these so important? It helps students with creating an organizational framework to help them connect knowledge from different disciplines. And I'll give you some examples of this in just a minute to show you how powerful it is. But really, the key here is you're helping students build like a set of glasses through which they can view the natural world. And if done correctly, the students can be presented with new, maybe novel or different concepts, and they'll be able to figure it out without ever seeing it before. That's important because otherwise you would, if you stick to the bottom level of Bloom's taxonomy, and it's all about memorization, rote memorization, basic levels of learning, then the only way the students would ever learn that particular answer to that question is if somebody told it to them and then they memorized it. Well, we don't want that. What we can do, though, is teach students how to think their way through a problem so that when you do put something new in front of them, they can figure it out. And I'll show you how that works. So first off, scale and proportion. We're just going to play with this cross-cutting concept for a second. Now, you can see a cube, and I've made it a little bit bigger than normal, so to you it's not going to look like the dimensions that I've put up here on the slide. But imagine that this cube had dimensions of 1 centimeter by 1 centimeter by 1 centimeter. Could you figure out what the surface area is? Can you remember the mathematical formula for that? In the United States, we teach that as length times width. That would help us get the surface area of one side. So if I take the length of 1 centimeter, times it by the width of 1 centimeter, 1 times 1 is 1. Then we multiply the units together, so the answer would be 1 centimeter cubed. But that cube, or not cubed, squared, I'm sorry. But that cube has 6 sides. So if one side is 1 centimeter cubed, then we multiply it by 6 to account for all the sides. So the surface area would be 6 centimeters cubed. For volume, we would times the length to the width to the height. 1 times 1 times 1 is 1. Times the units together, we would get centimeters cubed. So hopefully you came to that same conclusion. Now, I want you to notice that the surface area, 6, is a larger number than the volume, which is just 1. So the ratio 6 to 1 exists, with surface area being 6 times bigger than the volume. Now, what if we took that cube that's only this big and we made it 10 times bigger? We often see that in movies and things like that. If you're a fan of Harry Potter, perhaps, you might remember, I think it's in the third Harry Potter, The Prisoner of Azkaban, where we're introduced to the character of Aragog, and it's a large, large spider. It's almost as if the creators of the book and the movies just said, well, let's just take what we know as a spider, which is really just small, and make it 100 times bigger. Can you do that? Is that an okay thing? Would it work? Well, let's see. We're going to start off with something easy though, just a cube. So if we take a cube and just make it 10 times bigger, well, does the surface area and volume just get 10 times bigger? So our surface area is now 60 and our volume is 10? Well, let's see. If we do length times width, and now for surface area on the larger cube, 10 times 10, well, that's 100. So one side is now 100 centimeters cubed, or squared, I'm sorry. Then times it by the 6 sides. No, that larger cube, something weird has happened just by making it 10 times bigger. Notice my surface area is not 10 times bigger than the smaller cube, it's 100 times bigger. But look at the volume. Just by making the cube 10 times bigger, the volume has increased by a factor of 1,000. And now if we look at our ratio, the small block went from 6 centimeters to 1, or 6 to 1 ratio, to now we're 600 to 1,000. Notice our volume is huge compared to our surface area in the larger block. That's very interesting. Now you could just teach students this, show them the math in class, make them do some worksheets so that they know how to do the math. But is it going to stick? Well, let's see. Again, going back to these cross-cutting concepts, we're trying to help students make connections between multiple areas and then extend that newfound knowledge to new things that they've never seen before. So I'm going to do the same thing to you. Do you like motorcycles? I do. These are pictures. These are not my motorcycles, but I did own each of those motorcycles, except mine was black. My BMW motorcycle actually was that same color and everything, and I love it. But my very first motorcycle was this Honda Rebel that you see. And I want you to focus just on a few things on these motorcycles. Look at the engine. The Honda Rebel, the smaller engine, was a 250. That 250 is in reference to the size of the motor. 250 cc's is the displacement of the pistons, or cubic centimeters. My BMW is a 1200 cc's. So the motor, or the engine, in my BMW motorcycle is much, much bigger than in my Honda Rebel. Now, the reason why I got rid of my Honda Rebel, cruising around town, it was fun. But if I tried to take it on faster roads, didn't work. Top speed would be maybe 70, 75 miles an hour. And even climbing some of the mountains here in southern Utah, it just didn't do that well. Whereas my BMW, that thing is fast. And it is fun to drive. So having that bigger engine makes a big difference. But I want you to look at the design of the engine. Focus in on the Honda Rebel. Can you see these little fins metal outcroppings coming off of that engine? Do you know why those are there? Some of you might. And the answer is heat. As the engine is exploding gasoline, it's generating heat. The harder you work that engine, the more heat is given off. Now, how are you going to get rid of the heat? Well, in this case, the engine is small enough that the fins are going to help dissipate or exchange that energy from the engine to the cooler air around it. So if I can get air to flow through and in between those fins, then I have more surface area to get rid of heat. Does that make sense? Now the problem with my Honda also is I live in Cedar City, Utah. And if you've ever been here, you'll know that this time of year, the mornings get pretty cold. Often in the mornings, we're below 0 degrees Celsius. When I would jump on my old Honda Rebel and come to school, the engine just didn't work that well, kind of struggled. But my Beamer, my BMW, not a problem. The issue is this, my Honda Rebel engine, because of all the surface area, never really heated up and worked the way that it was supposed to. But my BMW engine, not a problem. But my BMW engine also does have some little decorative fins if you look closely at the bottom, but they're really there just for looks. You couldn't put fins big enough on a BMW engine of that size to have it air-cooled. So that means I've got to have more bells and whistles. I've got to have extra parts on my BMW motorcycle so that the engine can stay cool. In other words, that motor does not have enough surface area to cool itself properly. So I have to do something different in the design of that motor. It's a structure and function cross-cutting concept. The structure of my motor has to meet the function. And if the function is I need to dissipate heat, then I have to change the structure because of the different sizes of those engines. So in the case of the BMW, it's not air-cooled, it's liquid-cooled, and I have to have a radiator, a whole nother gadget put on the front of that motorcycle that gives me enough surface area that fluid can be passed through small tiny tubes and a lot of air rushes past it so that those tiny tubes can give off the heat from the engine to the air. It increases the surface area. That's what a radiator does. Now, once you know that process, the hope is that you could extend it to maybe areas you've never thought of before. So if I take time in my beginning biology classes helping students understand this, then I can throw new things at them like this. Why is the human kidney made up of 1 to 2 million microscopic little nephrons? Or why is the human lung not just one big sac like many students think that just inflates and deflates as you breathe, but it's actually this network of tubes that you can see off to on the slides? Well, the answer to both of those is exactly the same as the motorcycle. Surface area to volume ratios. You've got to get small so that you get enough surface area like that Honda Rebel. If you get big, you're going to have to come up with some other structures to handle it. In this case, both of these organs have figured out how to go small so that I can have the surface area I need to both filter blood and exchange oxygen and CO2 with my environment. All three of those things, motorcycles, kidneys, and lungs, all share that cross-cutting concept of structure and function. Now, we're going to put this all together, and I'm going to take you through one experiment that I do with my students. So we're going to put 3D, the three dimensions of science science education, into practice using a lab that's intended to help students understand osmosis. The typical osmosis lab, at least in the United States, is very cookbookish, which means we have predetermined concentrations of differing saline solutions, and you can see each of the different solutions with different amounts of salts in each of those beakers, and then we've got a special device that will core, in this case, a potato, so that we can have equally sized pieces of potato, and we do all of this thinking for the student. In some cases, we use dialysis tubing, but all of it's the same. We're telling the students how much salt to put in the beakers, how much water to put in the beakers, how big of a piece of the potato, and how long we're going to soak it, how to do everything. There's no option of failure, really, unless you just weren't paying attention to the recipe at all. Just simply follow the steps. What are you trying to teach in a classroom like this? To follow steps? Or do you want to foster thinking? I do things a little bit different. This is how I conduct my lab. I walk in, and at the beginning of the lab, I go up to the chalkboard or whiteboard at the front of the class, and I write down these 5 steps. I tell them, get in groups of 3 or 4. Come up, you get 1 potato, take it out of the bag. You can use anything in this lab, and I purposefully put stuff out on the cabinets and the countertops. Stuff that there's no way they should be using. But I put it out there anyway because they don't know that they shouldn't be using it. But I'll put microscopes and measuring tapes and beakers and hot plates and thermometers and everything, knives and just everything they would need and more. And then I tell them, your job is to do this. At the front of the class, I have 3 buckets. In those buckets, I've filled them up with water, usually about, 20 liters maybe. So a fair amount of water. And then I get a large container of just table salt. And in one container, I put about 3/4 of the salt in that container in one bucket, so that one bucket is really salty. In the middle bucket, I'll put just a little bit of salt. And in the last bucket, I don't put anything. But it's just water I got from the tap in the lab. So setup, really easy. Takes me 5 minutes. I'll mix the water a little bit to get the salt to mix in. And with those buckets that I do not label, I just put them at the front. I tell the students, your job is to do this. Tell me which bucket has the most salt, which one has a little bit of salt, and which one doesn't have any salt. But you have to use a potato to do it. You can't taste it or something like that. You have to get the potato to do something to help you understand which bucket has the most salt. You got 20 minutes to do it, and then often I will leave the classroom and say, it starts right now. Now, most of the time I will stay in the classroom, but I have found if I do stay, the students are always asking questions. My presence freaks them out a little bit. So if I leave for 5 minutes, sometimes I'll come back and students will say, hey, what about this? What about this? Can I do this? And usually my answer is, yeah, sure. If you think it'll work, go for it. And I'm always encouraging. Sometimes their ideas are horrible, but that's okay. Sometimes they want to do something a little dangerous, and I'll say, I don't know. So if there's a safety issue, I'll kind of stop that or help them. But this round one, this first little part, the first 20 minutes, is designed for them to try something, get creative, talk with their group, but most likely it's not going to work. Their experiment will fail, but that's a good thing. You'll see why. Now, the funnest part about round one is students will do the oddest things. This is an actual picture that I took where the students weighed the potato, just like that. When I ask them, what are you doing? They're like, well, we figured we should weigh something. That's what scientists do. Well, why are you weighing it? We don't know. We just want to know what the potato weighs. All right. I've had students cut up their potatoes, get the water from the buckets, put the water and the potato on the scale. Now think about what's happening here. If you have a known amount of water and a potato inside, and they put it on the scale, is it ever going to change weight? And what would it take for it to change weight? Evaporation is about the only thing out there. I've even seen students take a potato and shove a thermometer into it and then soak the whole potato because they thought that the salt would somehow change the temperature of the potato. They do the most interesting things, but often they rush into this without thinking about what they're doing. They just know that they need to do something. So I actually heard this: our potato is soaking, now what? The group never thought about how they were going to analyze the data. How are they going to know when, what means salty, what means a little bit of salt or not? They just do some very interesting things. As the instructor, you need to pay attention to what they're doing, because most of the time what they are doing is based in some type of a misconception that they've picked up over their life somehow. And it makes for a great classroom discussion right before round 2. The key is focus on what went wrong, but also focus on some of the good things that the students were doing in round 1. Now, when we analyze round 1 and we have them vote on which one is the saltiest, I just do a simple vote at the front of the classroom. In almost every case that I've done this over the last 12 years, we can't ever come to a consensus as a group on which one has the most salt and which one little salt and none. They all vote in weird ways because they're not quite sure what they're looking for. And that's okay. We build off of those and their misconceptions from round 1 to start a discussion among the classroom on what should we pay attention. And often I'll encourage them a little bit and I'll say, did you notice that this group over here peeled their potatoes, but you guys didn't peel your potato? Does that make a difference? And then we have a discussion. Or I might say, did you see the size of their potatoes in this group? Some of your potatoes were big, some were small, some were long and skinny. This group, you guys cut yours all up into perfect little cubes that are all the same size. Does that even matter? And then we have a discussion off of that. These discussions, eventually, we will cover everything from size of the potato, the shape of the potato, the weighing technique, how long did you soak it, do you leave the peel on, and many other things, until they start to see, oh yeah, these things do have an impact, and we need to do a better job. And so when I tell them we're going to do another round, only we're going to come up with a system that all of us are going to use together. Everyone's going to do the exact same process, but we have to all decide what that's going to be. And so on the board, I let them come up with answers. So often they'll say, everyone's got to peel it. Let's all come up with the same size. Okay, what size do you want it to be? They might pick dimensions of 1 centimeter by 1 centimeter by 1 centimeter. Or they may say it's all got to be a certain shape or a certain weight or whatever. It doesn't matter as long as everyone's doing the same thing. Once we all have the new techniques down, the new protocols, we redo the experiment with new potatoes and new water. So they'll go clean everything up, go get fresh water out of the buckets. Well, not fresh, but salty water, a little bit of salt and no salt. But the key is they're all individually trying to do the same thing. Then at the end of the soaking time, which they determine, we analyze the data. I will actually create an Excel spreadsheet where the groups come up, they type in their data, and then we can analyze it together as a group and see the differences in the salt concentration. Now, this is just one class. It doesn't always look like this. Sometimes buckets A and B are closer together, or B and C, and we have a discussion about how much difference is difference enough to be able to statistically, with confidence, say that there is a difference between these buckets. Because sometimes one bucket you can say, yes, that's the fresh one, and then the other two, they might be so close that we're like, we don't know. And we'll talk about how our lab technique could have been the source for the width of those error bars that you can see on the slide. But the point is, it leads to a really good discussion. Now, with round 2 done, hopefully they're starting to see and understand the importance of doing all these little steps and paying attention to the details, like shape and peel and stuff like that. So then we get to come to the fun part, and that's round 3. So in round 3, this is we call it the potato derby. Everyone gets one potato, well, every group gets one potato. They have to design a potato that cannot weigh more than 10 grams, plus or minus 0.1 grams, but they can design it in any shape that they want. And they can use any material in the room that I have access to soak it in and to prepare their potatoes. And I give them usually about 10 minutes to come up with their design and get everything ready to go, and then we soak them all at the same time. I will have them weigh it on a scale in front of me so that I can verify that it does weigh 10 grams, plus or minus 0.1 grams. And then we let it soak in whatever fluid they want to soak it in. And I've had students do some pretty interesting things. Some of them will just use tap water from the sink. Some of them will use water from the buckets, which I don't know why they would do that. I've had some students take fluids out of their own backpacks. They might have had like a Gatorade with them, a sports drink, or Red Bull, or something like that. And they thought, I even had one student who had beer with him. I don't know why he was carrying around a beer, but he did. And they used that. And they would ask me, is it okay if we soak our potato? And I have to hide kind of the laughter in my eyes and think like, oh, maybe it's a good idea. And I'm, oh yes, of course, you can soak this in beer. Or Gatorade, because apparently they think it's a good idea, not understanding that there's other groups who realize distilled water is the best way to go. And in our lab, we actually do have distilled water. Some students will figure that out. Some students will also figure out that we have hot plates in the lab, and that warm water will speed up the diffusion or the osmotic rate of the water going inside the potato. They get really, really into this. Partly because there are prizes on the line. I have king-size candy bars for the winners. They also get sneaky. So you can see these students have set up books to hide what they're doing so that other groups can't see what they're doing. They also get incredibly creative. And the whole reason is they're playing, they're having fun, and they have ownership over their idea. It wasn't me telling them to do something. So it's just fun to watch the students come up with these ideas. Some are going to just fail miserably, and others are going to be spectacular. Here's just one example of one classroom and the potatoes that they designed. Some of them obviously look like stars, and some look like sponges, and I mean, they're just all sorts of crazy things. I can tell that this group, except for maybe that one square one on the bottom, that this group really understood that concept of surface area to volume, and that anything they could do to optimize the surface area would help with absorbing water. I've had students make perfect little balls, which means they didn't get it. That's the worst they could possibly do. And also some students will even do things like when they're soaking it in the beer or the Gatorade or something like that, when they weigh it at the end and we're all weighing it in front of the class and they're like, oh, what are we going to get? What are we going to get? The student who had theirs soaking in beer, when they weighed it, it weighed less than what they started with. And the students were like, what? How did it lose weight? And I'm like, well, you soaked it in alcohol. And they're like, yeah, but that's alcohol, it's supposed to suck it up, because when I drink with my friends, I can drink lots of beers. And I'm like, well, but it's actually, beer is a diuretic. Alcohol is a diuretic. It's going to pull the water out of your cells. So you're going to end up urinating a whole lot later that night, and you'll actually urinate out more water than you actually brought in through your beer. And that's when learning happens, because you can watch students' faces go, wait, my cells are losing water, so I'm actually getting dehydrated when I drink with my friends? Yeah. Oh. Is that why I have a hangover in the next morning? And I'm always so thirsty? Yeah. And it makes a connection. That's what we're going for in science education, that connection. And it's fun to watch them see that Gatorade has electrolytes in it. It's not going to absorb into the cells as good as distilled water is, and especially warm water. So it's fun to let the students kind of reveal their secrets, and that's kind of the self-assessment that we're looking for. And the key is also, the struggle is great for the classroom, but also it's less work for me, and it's way more fun for both me and the students. I don't have to set up all these beakers and stuff as I did once before. I get to let them play. And for me, that makes it all worth it. Now, big picture ideas. What we're aiming for is to design a classroom where we don't always have to hold the hands of our students and instruct them in everything that they're trying to do. Let them work in groups, like really work in groups where they can obtain information, maybe search the web for ideas, they can talk back and forth, they can really engage in whatever it is they're trying to devise. This process also helps deepen their understanding of the process of science, that this is what scientists do, that it's fun, it's not just cookbook. There's a lot of creativity in science. That's what we're trying to show these students. And also, they get introduced, at least at this beginning level, to very, very basic statistics, more than just finding averages, but we will usually move on to standard deviations and things like that. So they get to see how math gets brought into a biological setting like this. Now, some take-home thoughts. Did you notice the 3D pieces in the lab that we just talked through? Did you notice that the students did the work and that it wasn't me? Now, on those 3D pieces, the students were planning and carrying out their own investigation. They were obtaining and evaluating and communicating their data. There's the science and engineering practices. Cross-cutting concepts, it's all about scale and proportion, structure and function, patterns. We're bringing in all sorts of cross-cutting concepts there. And then the disciplinary core idea is hopefully they're understanding something about osmosis and how surface area to volume ratios can influence the structure and function of everything from the renal system to like kidney design as well as lung design. But also I can throw interesting questions at them, like on a really cold evening and you want to jump in bed. When you jump in bed, if your covers are also cold, do you curl up into a ball? If you do, why do you do that? And if a student can go, wait, by curling up into a ball, that means you're reducing your surface area and you're maximizing your volume. So by reducing your surface area, you keep more of the heat right around you. Nice. See, I didn't have to teach that to them, nor did they have to memorize it. I can just throw interesting new things at them as I go through my biology courses. And by the end of the semester, because they have those glasses built in for their cross-cutting concepts, by the time we do get to the renal system or the digestive system, and I say, oh, look, in the small intestine, not only does the small intestine, is it small, but there's little finger-like projections called villi. And those villi also, there's circular folds in there. And on top of the villi, you've got little microvilli. Why? And the students just quickly dismiss it, like, that's easy. Surface area to volume, it's a structure and function thing. It's no different than us designing our potatoes. Genius. That's how you know learning has happened, is I don't have to explain everything. And that's the point of the new 3 dimensions of science put forth by the next generation science standards. And I know all of you are education students or going into teaching, at least that's what I was told. So I want you to pay attention to how you design your classroom. Are you going to make room for failure? Maybe reimagine how you were taught and see if you can come up with a way to put the responsibility on the students. Bring some more play into your classroom. Let your classroom get loud. Let talking happen, laughing and joking, because they're still doing the work. They're just getting more out of it. And that's what I've got. I hope you found this interesting and that you learned something new. Good luck in your future endeavors, especially as teachers.